Welcome. This is Dr. Sudha, Associate Professor, Department of Mathematics, Rupatunga University. In this session, let us see some lemmas on stabilizers and the famous Cauchy-Frobenius theorem. The first lemma states that if G acts transitively on a set S, then the stabilizers of the elements of S are conjugates. That is, if you take any two stabilizers of elements of S, we need to show that are conjugate. So let G act transitively on S. There exists X belongs to S such that Gx is equal to S. Since the group action is transitive, so for some X belonging to the set S, there is a stabilizer Gx which is equal to the set S. That is, S is equal to set of all images under the function f from G cross S to S defined as f of G comma X as Gx for all G belonging to G. Now to prove that for any two elements X and Y, stab X and stab Y, that is the stabilizer of X and stabilizer of Y are conjugates. So let us take A belonging to stabilizer Y. Since A belongs to the stabilizer Y, it fixes Y. Therefore, AY is equal to Y. From here, we can write A into Gx is equal to Gx because Y belongs to S and the group action is transitive. And we have taken S is equal to Gx for some X. So Y belongs to Gx. And this implies Y can be written as some 1G into X where G belongs to G. So we can replace Y by Gx and we get A into Gx is equal to Gx. By operating by G inverse from the left side, we get G inverse A into Gx is equal to G inverse Gx. G inverse G gives us E. E into X is X. And combining the first three elements here, we get G inverse AG into X is equal to X. So this element G inverse AX is fixing X. So since it fixes X, it must belong to the stabilizer of X. Therefore, G inverse AG belongs to stab X. Since this element belongs to stab X, now by operating by G from left side and G inverse from right side, we can show that A belongs to G into stab X into G inverse. Since all the steps are reversible, we can say that A belongs to stab Y implies if and only if A belongs to G stab X into G inverse. Therefore, the two sets, that is stab Y and G stab X stab X into G inverse are equal. So since this equation is obtained, we can say that the two stabilizers, that is stab Y and stab X, are conjugates. Now let us move on to the other lemma. Let S be a G set, that is the group action of the group G on S, and tilde be an relation on S, that is for X and Y belonging to S, X is related to Y if and only if Y can be written as Y is equal to Gx for some G belonging to G. Then stab X is isomorphic to stab Y, and this follows, this gives us stab order of stab X is equal to order of stab Y. So given G is a G set, that is we have a mapping from G cross S to S. And it is defined as the order pair G comma S is taken on to G into S. Now let us take two elements X and Y in S. If X is related to Y, then there exists a G belongs to G such that Y is equal to Gx. Now operating by G inverse from the left side, we get G inverse Y is equal to X. Now let us consider an element A belonging to stab X. So A fixes X. So AX is equal to X. Whereas X is G inverse Y. On substituting that, we get A into G inverse Y is equal to G inverse Y. Now operating with G from the left side, we get GA G inverse into Y is equal to Y. Therefore, this element GA G inverse fixes Y. Therefore, this GA G inverse must belong to stab Y. Since this belongs to stab Y, now operating by G inverse from the left side and G from the right side, we can show that A belongs to G inverse stab Y into G. So whenever A belongs to stab X, so we can say that GAG inverse belongs to stab Y. Now let us define a mapping phi from stab X to stab Y by phi of A is equal to GAG inverse. For this, we are using this expression, which is obtained by A belonging to stab X implies GAG inverse belongs to stab Y. To show that phi is well defined, let the two images phi of A is equal to phi of B. By the definition of phi, this can be written as GAG inverse is equal to GBG inverse. Since all these elements belong to group G, we can use cancellation laws and we can write A is equal to B. Therefore, phi is well defined. Now, let us show that if B belongs to stab Y, that is, we will need to show that it is an onto mapping. Let us take B belonging to stab Y. So By is equal to Y because B fixes Y. And we have Y is equal to Gx because X and Y are related. So B into Gx is equal to Gx. So which implies G inverse By is equal to X is equal into X is equal to X. This is obtained by operating by G inverse from the left side and we obtain this expression. Since this element fixes X, G inverse G must belong to stab X. For B belonging to stab Y, we have found out G inverse G belongs to stab X. So let us find the image of G inverse BG under the mapping phi. So it is mapped down to G into G inverse BG into G inverse. So here GG inverse and GG inverse here will give you E and finally we obtain B. Therefore, phi is 2. Now to show that phi is a homomorphism, let us consider phi of AB. So that gives us G into AB into G inverse. We can certainly insert one E in between A and B. For that E, we can substitute G inverse G. Combining the first three elements, we obtain phi of A, and the last three elements will provide phi of B. Hence, phi is a isomorphism. Since it is a homomorphism, it becomes a isomorphism. Therefore, the domain and the codomain are isomorphic, that is stab X is isomorphic to stab Y. Certainly, from here it follows that cardinality of stab X, that is order of stab X is equal to order of stab Y. Hence the theorem. Next, let us move on to Cauchy-Frobenius theorem. The statement goes like this: let G be a finite group acting on a set S, that is S is a G set, and K denote the number of orbits in S under G. Then K will be equal to 1 over order of G into summation over the elements of G of order of SG, where SG is denoted by the set of all X belongs to S, such that Gx is equal to X. Now with this data, let us define one set T, which contains all ordered pairs G comma X, such that Gx is equal to X. That means here G is fixing X. Certainly, this set will give us the stabilizer of X. And let the order of T be equal to capital N. Now, for each G belongs to G, there are order of SG pairs having G as the first member. That is nothing but the sets of the type. If I consider the order pairs, some G into X such that Gx is equal to X, How many of them are there? There are order of SG pairs. Therefore, capital N will be equal to summation order of SG where G runs over capital G. On the other hand, for each x belongs to S, here we took for each G, that is the first element in the set T. Now let us take for each x where x is the second element in the set T. There are order of stab x pairs having x as the second member. Since gx is equal to x, this G definitely belongs to stab x because it fixes x. Therefore, the sets of the type G comma X where Gx is equal to X. Therefore, N can be taken as summation order of stab X where X belongs to S. But in orbit stabilizer theorem, which we discussed in the previous session, we have order of stab X is equal to order of G divided by order of the orbit of X, that is OX. Now for order of stab x, we can substitute order of G divided by order of orbit of X. Therefore, N will be equal to summation order of G divided by order of OX, where X runs over the set S. Since X runs over the set S, this order of G is common in each and every term of this summation. One can remove order of G as common. So we get summation 1 over order of OX, and let us name this as 2. But if I take this 1 over order of OX, this has the same value for all x in the same orbit. This we need to remember, all x in the same orbit. If they belong to two different orbits, the values will change. If they belong to the same orbit, then this 1 over order of OX remains the same. Therefore, let us take this summation 1 over order of OX, where x runs over S is equal to some k. Therefore, we obtain N is equal to order of G into K. Now, K, when we express K in terms of N, so we get 1 over order of G into summation order of SG, where G belongs to G. So this is the value of N which we obtained in the previous steps. Hence the Cauchy-Frobenius theorem. Thank you.